Right now, you are traveling through a universe filled with places that would erase you from existence in less than a second. You cannot see them. You cannot hear their approach. But scattered across the cosmos are objects so violent, voids so empty, and forces so overwhelming that your atoms would be ripped apart, your molecules shredded, your entire world reduced to radiation before you could register what was happening. This is the scariest places in the universe explained, and compared to the cosmic horrors that lurk in the darkness between stars, every nightmare you have ever imagined is gentle. We will journey from magnetars capable of tearing matter apart at the atomic level to voids so empty they defy the laws of cosmic structure. We will witness gamma-ray bursts that could sterilize Earth from halfway across the universe. We will explore rogue planets wandering alone through eternal darkness and black holes so massive they bend the fabric of reality itself. If you enjoy this journey through cosmic terror, consider subscribing. Prepare yourselves, we begin. 330 million light-years from Earth, there exists a region of space that should not be possible. Scientists call it the Butter's Void. Inside this incomprehensible emptiness, where cosmologists expected to find 2,000 galaxies clustered together by gravity's patient pull, there are 60 galaxies scattered across a volume so vast that if you placed our Milky Way at its center, the nearest neighboring galaxy would be invisible to the most powerful telescopes humanity has ever built. This is not empty space in the way we understand it. This is a hole in the universe's structure, a cosmic wound carved into the very fabric of existence where galaxies fled or never formed at all. Robert Kirshner discovered this impossibility in 1981 while mapping the distribution of galaxies across the observable universe. What his team found violated everything astronomers understood about how matter distributes itself across cosmic scales. Gravity pulls, matter clumps, structure emerges from chaos as galaxies gather into clusters. Clusters merge into superclusters, and superclusters weave themselves into the cosmic web. But the Butter's Void represents the opposite. It is a region where the cosmic web tore, where the universe said no. The void spans 330 million light-years across. If you could somehow position yourself at its center and look outward in any direction, you would see nothing. No stars, no galaxies, no light from distant quasars painting the darkness with ancient photons. Just emptiness extending farther than light itself has traveled since the first stars ignited. This is not the peaceful emptiness of space between stars in our galaxy. This is the loneliest place in the observable universe, a cosmic desert where even gravity seems to have abandoned its post. Scientists still debate what created the Butter's Void. Some propose that quantum fluctuations in the infant universe seeded regions of slightly lower density, and as the cosmos expanded, these regions grew into supervoids, while matter rushed away toward denser areas. Others suggest we are witnessing the aftermath of a cosmic catastrophe we cannot yet comprehend. Something that cleared galaxies from this region like a hand sweeping pieces from a chessboard. The void is not unique. Astronomers have discovered others. The local void, the Eridanus supervoid. Empty regions scattered throughout the cosmos like bubbles in foam, but none match the Butter's Void's combination of size and emptiness. None inspire the same existential dread. Imagine existing inside such a place. Imagine a civilization arising on a planet orbiting a star in one of the Void's 60 galaxies. Their astronomers would look outward and see nothing. No neighboring galaxies to study. No cosmic neighbors to wonder about. just darkness extending in every direction for hundreds of millions of light years. They would be alone in a way we cannot truly comprehend. Our Milky Way belongs to a cluster. That cluster belongs to a supercluster. We are embedded in structure, but a civilization inside the Boötes void would see only isolation. They might conclude they were the only galaxy in the entire universe. They might never discover that beyond the impossible emptiness surrounding them, the cosmos teems with structure. The void's existence raises disturbing questions. If regions this empty can form naturally, what prevents larger voids from emerging? What stops the universe from developing emptiness on scales that dwarf even the Boötes void's 330 million light-year expanse? Cosmologists studying the void's properties discovered something unsettling. The void is expanding. As the universe itself expands, the emptiness grows. Galaxies at the void's edges accelerate away from the center, driven by dark energy's relentless push. The loneliest place in the universe is becoming lonelier. But the Boötes void represents just the beginning. The universe contains horrors far more violent than empty space. Objects that do not simply lack matter, but actively destroy it. Forces that do not create voids through absence, but through annihilation. Scattered across the cosmos are magnetars, neutron stars with magnetic fields so powerful they warp the quantum vacuum itself. There are gamma-ray bursts, cosmic laser beams that could sterilize our planet from billions of light years away. There are black holes so massive that calling them supermassive feels inadequate. Places where physics breaks down and mathematics surrenders. These cosmic horrors share one thing in common. They operate on scales and with forces that render human comprehension meaningless. A magnetar's magnetic field strength is not simply very strong. It is 100 trillion times stronger than Earth's magnetic field. A gamma-ray burst does not release a lot of energy. It releases more energy in 10 seconds than our Sun will produce over its entire 10 billion year lifespan. A supermassive black hole does not have a lot of mass. It contains the mass of tens of billions of suns compressed into a region smaller than our solar system. These are not differences of degree, they are differences of kind. The universe we inhabit is not hostile. Hostility requires intention. The cosmos is simply indifferent. It contains regions and objects that would obliterate us not through malice, but through physics. A magnetar does not choose to rip atoms apart. That is simply what happens when magnetic fields reach strengths that should not exist. A gamma-ray burst does not aim at Earth. It simply exists, a consequence of a hypernova's death throes, and if we happen to lie in its path, our atmosphere becomes plasma. A void does not swallow galaxies deliberately. It simply marks a region where, for reasons we still struggle to understand, matter chose not to gather. What follows is a journey through these places, not a catalogue of cosmic phenomena, but an exploration of what exists at the absolute limits of physical law. We will examine objects that challenge our understanding of what the universe allows. We will visit regions so extreme that describing them requires mathematics most humans will never encounter. We will confront the disturbing reality that we exist only because we are not close to any of these places, that our survival depends entirely on cosmic geography, that one light year in the wrong direction, one parsec closer to the wrong object, would mean our planet never formed, our sun never ignited, or our solar system was sterilized before life's first molecules assembled. But what lies beneath this apparent catalogue of cosmic violence is far stranger than isolated dangerous objects scattered through space. At the very edge of what physics allows, something impossible spins through the Milky Way at 110,000 miles per hour. You cannot see it with your eyes. Most telescopes struggle to track it. But SGR 0501 plus 4516 exists, a stellar corpse racing through space with a magnetic field so powerful it defies every intuitive understanding of what magnetism means. This is a magnetar, a neutron star that took the concept of magnetic strength and pushed it past the breaking point of reality itself. Its magnetic field measures 100 trillion times stronger than Earth's, and if it passed within half the distance from Earth to the Moon, it would rip every atom in your body apart. Magnetars represent what remains after certain massive stars explode. When a star between 10 and 25 times our Sun's mass exhausts its nuclear fuel, its core collapses in less than 1 second. Electrons merge with protons, forming neutrons. Matter compresses until a mass greater than our Sun occupies a sphere just 20 kilometers across. The star's magnetic field, previously spread across millions of kilometers, compresses with it. The mathematics is straightforward. Conservation of magnetic flux means that, as the star's radius decreases by a factor of 100,000, the magnetic field strength increases by a factor of 10 billion. But some neutron stars take this process further. Scientists discovered the first magnetar in 1998. Astronomers at the Rossi X-ray Timing Explorer detected bursts of X-rays from an object designated SGR 1900 plus 14. The bursts repeated. They pulsed with precise regularity every 5.16 seconds. But the energy output made no sense. Normal pulsars, rotating neutron stars that beam, radiation, like cosmic lighthouses, draw their power from rotational energy. As they spin, they slow down. The SGR object was slowing down, but far too quickly. It was losing rotational energy at a rate that suggested something else powered its radiation, something more violent. The answer emerged from detailed analysis of the object's spin-down rate. Only one mechanism could account for the energy output: an impossibly strong magnetic field decaying over time, releasing energy as magnetic field lines reconnected and snapped. Physicists calculated the field strength required: 1 quadrillion Gauss. For comparison, Earth's magnetic field measures 0.5 Gauss. A hospital MRI machine generates 15,000 Gauss. A magnetar's field strength is 10 billion times greater than the most powerful sustained magnetic field ever created in a laboratory. It is a magnetic field so intense it warps the quantum vacuum, creating virtual particles from empty space. SGR 0501 plus 4516, the magnetar racing through our galaxy at 110,000 miles per hour, represents an extreme example even among these extreme objects. Researchers at the European Space Agency tracked its motion using the XMM Newton Space Telescope. The magnetar is not orbiting the galactic center in a stable circular path like most stars. It is escaping. Something accelerated this 20-kilometer sphere of neutrons to a velocity that will eventually carry it out of the Milky Way entirely. Astronomers suspect it received this kick during the supernova that created it, when asymmetric collapse launched the newborn magnetar across space like a bullet from a cosmic gun. The danger a magnetar represents is not hypothetical. Its magnetic field does not simply attract or repel. At strengths exceeding 1 billion Gauss, magnetic fields begin to affect matter at the atomic level. Atoms are not solid spheres but quantum clouds of electrons surrounding nuclei. Those electron clouds have shapes. In normal environments, atoms assume their lowest energy configurations: spherical for some elements, elongated for others. But in the presence of a magnetar's magnetic field, atoms stretch. Electron clouds distort into needle-like shapes aligned with the field lines. Chemical bonds break. Molecular structures collapse. The very geometry of matter changes. If you somehow approached within 1,000 kilometers of a magnetar's surface, the effects would begin before you realized what was happening. The iron in your blood would align with the magnetic field. But iron atoms are embedded in hemoglobin molecules, which are embedded in red blood cells, which flow through vessels. The magnetic torque trying to rotate those atoms would tear molecular bonds apart. Your hemoglobin would denature. Your cells would rupture. This would occur throughout your entire body simultaneously. There would be no pain. The signals your neurons would attempt to send would fail because the sodium and potassium ions responsible for nerve impulses would themselves be distorted past functionality. At 100 kilometers from the surface, stranger effects dominate. The quantum vacuum itself responds to magnetic fields this intense. According to quantum electrodynamics, what we perceive as empty space is not truly empty. Virtual particle-antiparticle pairs constantly appear and annihilate. In normal space, they exist for such brief moments that they remain undetectable. But a magnetar's magnetic field polarizes this quantum foam. Virtual particles stretch along field lines before annihilating. This process, called vacuum birefringence, means that empty space near a magnetar behaves like a crystal. Light passing through it splits into two polarizations traveling at different speeds. Space itself becomes optically active. The magnetar's surface presents conditions that make these effects seem mild. Surface gravity measures 200 billion times Earth's gravity. If you could somehow place a marshmallow on a magnetar's surface, it would weigh as much as the Great Pyramid. The pressure would compress the marshmallow into a layer of degenerate matter thinner than a human hair. But you would never reach the surface. Long before you arrived, the tidal forces would intervene. Magnetars, like all neutron stars, are small, 20 kilometers across. At that size, the gravitational field strength changes significantly across distances measured in meters. Your feet, slightly closer to the magnetar than your head, would experience noticeably stronger gravity. The tidal force would stretch you, then tear you apart, then compress the individual pieces into streams of atoms, then crush those atoms into neutronium. Scientists studying SGR 0501 plus 4516 discovered something unsettling about its magnetic field. The field is decaying. All magnetar fields decay over time as magnetic field lines reconnect and release energy as X-rays. But this particular magnetar is decaying unusually quickly. Measurements suggest its magnetic field has decreased measurably over the past decade. As it decays, it releases starquakes. The neutron star's crust, a crystalline lattice of neutrons locked in place by quantum degeneracy pressure, cracks under the stress of the shifting magnetic field. Each crack releases more energy than all of humanity has produced throughout our entire existence. The X-ray burst travels outward at light speed, a spherical shell of radiation expanding through space. In March of 2004, another magnetar, designated SGR 1806-20, demonstrated what happens when a magnetar experiences a catastrophic starquake. The object, located 50,000 light-years from Earth, released a burst of gamma rays and X-rays so intense it affected Earth's ionosphere. For 1/10 of a second, this object 50,000 light-years away released more energy than our Sun produces in 150,000 years. The burst saturated every gamma ray detector in the solar system. If SGR 1806-20 had been located 10 light-years from Earth instead of 50,000, the burst would have stripped away our ozone layer, exposing the surface to lethal ultraviolet radiation. Complex life would have ended. Astronomers estimate our galaxy contains approximately 30 million neutron stars. Most are ordinary pulsars. Perhaps 10% are magnetars. That suggests 3 million magnetars exist in the Milky Way alone. Most are invisible, their radiation beams pointed away from Earth, their surfaces cooling over millions of years as their magnetic fields decay. But some remain active. Some still experience starquakes, and they are moving. SGR 0501 plus 4516 races through space at 110,000 miles per hour. Other magnetars follow different trajectories. They orbit the galaxy, cross spiral arms, pass through molecular clouds, and we cannot predict where they all are. The closest known magnetar to Earth is one E1647.0-5408, located 9,000 light-years away in the constellation Sagittarius. 9,000 light-years provides comfortable distance. Even if it released a burst comparable to the 2004 event, Earth would remain safe. But magnetars are difficult to detect unless they are actively bursting. There may be closer examples that remain dormant, their magnetic fields decaying quietly, their surfaces radiating only in wavelengths our telescopes do not routinely monitor. A magnetar could exist 1,000 light-years from Earth, invisible, waiting for tectonic stress to trigger its next starquake. This represents the first category of cosmic horror, not ancient, not distant in time, present, active, scattered through our galaxy like mines floating in an ocean. Objects that could, through no malice but simple physics, release enough energy to affect our planet from distances measured in thousands of light-years. And they are not the worst thing the universe contains. What comes next operates on even greater scales with even more devastating precision. 5 billion light-years from Earth, something died. The death took seconds. The announcement took 5 billion years to arrive. On January 14, 2019, detectors aboard the Neil Gehrels Swift Observatory registered a flash of gamma rays originating from a point in the constellation Fornax. The signal lasted 83 seconds. During those 83 seconds, the dying object released more energy than 1,000 suns will produce over their entire 10 billion year lifetimes. Astronomers designated the event GRB 190114C. It remains the most energetic gamma ray burst ever directly observed, and if it had occurred in our galaxy, pointed at Earth, you would not be reading this. Nothing on our planet's surface would have survived. Gamma ray bursts represent the universe's most efficient killing mechanism. They are cosmic laser beams, jets of plasma and radiation accelerated to 99.99% of light speed, focused into cones less than 10 degrees wide. They originate from two types of catastrophic events. Short bursts lasting less than 2 seconds emerge when neutron stars collide. Long bursts, persisting for seconds or minutes, mark the deaths of massive stars in hypernovae explosions. Both scenarios share one requirement: extreme rotation. As the stellar core collapses, conservation of angular momentum spins it faster. Material falling inward encounters the centrifugal barrier and rebounds outward along the rotation axis. The result is a jet, 2 jets actually, streaming in opposite directions, and anything caught in their path faces annihilation. GRB 19011 4C released photons with energies exceeding 1 tera-electron volt. For perspective, visible light photons carry energies measured in electron volts. A typical X-ray photon might reach 10,000 electron volts. Medical radiation therapy uses photons with energies up to 20 million electron volts. The photons from GRB 190114C exceeded 1 trillion electron volts. They were gamma rays so energetic they required detection techniques borrowed from particle physics. When these photons struck Earth's atmosphere, they created cascades of secondary particles. Each photon converted its energy into electron-positron pairs, which radiated more photons, which created more pairs, producing avalanches of particles detectable at ground level. Scientists using the magic telescopes in the Canary Islands measured photons from the burst arriving with energies up to 1.2 tera-electron volts. These photons had traveled 5 billion light-years through intergalactic space. They had passed through the cosmic microwave background radiation. They had traversed regions filled with distant galaxies, dust clouds, and magnetic fields. Yet they arrived at Earth with energies intact, moving at light speed, carrying information about an explosion that occurred when the universe was less than 2/3 its current age. The detection represented the highest energy photons ever observed from a gamma-ray burst. It also demonstrated something disturbing. Even from 5 billion light-years away, gamma-ray bursts remain detectable, which means at closer distances, they remain lethal. Physicists modeling gamma-ray burst effects on planetary atmospheres have established kill zones. If a typical long-duration gamma-ray burst occurred within 6,000 light-years of Earth, aimed directly at our planet, the initial gamma radiation would reach us traveling at light speed. There would be no warning, no time to prepare. The gamma rays would strike the upper atmosphere and begin creating that cascade of secondary particles. The atmosphere would absorb most of the primary radiation, protecting the surface. But in absorbing the radiation, the atmosphere would change. Nitrogen and oxygen molecules would ionize. Chemical reactions would accelerate. And within hours, those reactions would produce nitrogen oxides at concentrations high enough to destroy the ozone layer. Without ozone, ultraviolet radiation from the sun reaches the surface unfiltered. DNA molecules absorb UV light. The energy breaks chemical bonds. In small doses, cells repair the damage. In large doses, repair mechanisms fail. UV radiation at the intensities that would reach Earth's surface following ozone layer destruction would prove lethal to most surface life. Plants would die. Phytoplankton populations would collapse. The base of the food chain would disappear. Complex ecosystems would unravel. A gamma-ray burst does not need to directly irradiate the surface to cause extinction. It needs only to remove the atmospheric shield that protects life from the star that sustains it. The 6,000 light-year kill zone represents the distance for complete ozone destruction. Partial effects extend farther. At 10,000 light-years, a gamma-ray burst would still damage the ozone layer significantly. At 20,000 light-years, measurable effects would occur. Our galaxy spans 100,000 light-years. That means a gamma-ray burst anywhere within 1/5 of the Milky Way's diameter could threaten Earth if properly aimed. And gamma-ray bursts occur in our galaxy. Astronomers estimate the rate at 1 per million years. Those are not comfortable odds stretched across geological time. Some researchers have proposed that gamma-ray bursts explain certain mass extinctions in Earth's fossil record. The Ordovician extinction, which occurred 445 million years ago, eliminated 85% of marine species. The extinction shows patterns consistent with ozone depletion. Species living in shallow water, exposed to maximum UV radiation, suffered more than deep water species. Land plants, protected by being underwater, during part of their life cycles, survived better than purely aquatic organisms. The pattern suggests something removed atmospheric protection. A nearby gamma-ray burst remains a candidate explanation. Not proven. Not disproven. Simply possible. The most dangerous gamma-ray burst scenario involves not distance, but proximity. Eta Carinae, a massive stellar system 7,500 light-years from Earth, represents a hypernova candidate. The primary star contains 100 to 150 solar masses. It is unstable. In 1843, it underwent an eruption that briefly made it the second brightest star visible from Earth despite being 7,000 light-years away. That eruption released as much energy as a typical supernova, but the star survived. Astronomers studying Eta Carinae believe it will eventually collapse in a hypernova explosion, and when it does, it may produce a gamma-ray burst. The critical question concerns Eta Carinae's rotation axis. Gamma-ray bursts emerge along the rotation poles. If Eta Carinae's axis points at Earth within 10 degrees, the resulting burst could affect our planet. Current measurements suggest we are not directly in the line of fire. The star's rotation axis appears offset by at least 30 degrees from our direction, but stellar rotation axes can change. Precession occurs. Mass ejections alter angular momentum. The star is not stable, and 7,500 light-years places it comfortably within the danger zone for a direct hit. We are safe only because we are not directly targeted. That safety depends on geometry, not distance. GRB 080916C, detected in September of 2008, provided the most distant gamma-ray burst ever confirmed. It originated 12.8 billion light-years from Earth. The light traveling from that burst began its journey when the universe was just 630 million years old. Stars barely existed. Galaxies were still forming. Yet even from that incomprehensible distance, across 12.8 billion light-years of expanding space, the gamma rays reached us detectable. The burst itself must have been extraordinarily powerful. Calculations suggest it released energy equivalent to 9,000 supernovae exploding simultaneously. For several seconds, this single event outshone every other object in the observable universe. Gamma-ray bursts concentrate energy with terrifying efficiency. A supernova releases approximately 10 to the 51 ergs of energy. Most of that energy emerges as neutrinos, which interact so weakly with matter they pass through Earth as if it were empty space. A small fraction becomes kinetic energy in the expanding shell of gas. An even smaller fraction becomes visible light. But a gamma-ray burst channels a comparable amount of energy into two narrow jets. Instead of radiating energy spherically in all directions, wasting it across the entire sky, a gamma-ray burst focuses it into cones covering less than 1% of the celestial sphere. The energy density in those jets exceeds anything else the universe naturally produces. The jets themselves move at relativistic speeds. Measurements of jet velocities in observed gamma-ray bursts consistently show Lorentz factors exceeding 100. A Lorentz factor of 100 corresponds to 99.995% of light speed. At these velocities, special relativity effects dominate. Time dilation means that, from the perspective of matter in the jet, the journey across interstellar space occurs in fast forward. A jet traveling at 99.995% light speed experiences time passing 100 times slower than stationary observers. A journey that takes 100 years in the galaxy's reference frame takes 1 year for the jet. But the jets do not travel forever. They plow into the surrounding interstellar medium. Gas and dust slow them. They spread. They cool. The gamma radiation shifts to X-rays, then visible light, then radio waves as the shock front expands and cools. This afterglow can persist for days or weeks, allowing telescopes to pinpoint the burst's location and study its host galaxy. GRB 190114 C's afterglow was visible for months. Astronomers worldwide pointed instruments at the fading source, gathering data on the jet's composition, the density of surrounding material, the magnetic field strength. Each measurement refined models of what happens when massive stars die violently. These observations revealed something unexpected. Gamma-ray bursts occur preferentially in certain types of galaxies. Small, irregular galaxies with active star formation host more bursts than large, stable spiral galaxies. The correlation makes sense. Massive stars, the progenitors of long gamma-ray bursts, form in regions of vigorous star formation. They live short lives, just a few million years, then explode. They do not have time to migrate far from their birthplaces. So, gamma-ray bursts trace regions where stars are currently forming. Our Milky Way forms stars at a modest rate. Galaxies hosting observed gamma-ray bursts often form stars 10 or 100 times faster. We are, statistically, safer than civilizations in more active galaxies, but statistics offer cold comfort when discussing extinction mechanisms. The galaxy has existed for 13 billion years. Even at one burst per million years, that suggests 13,000 gamma-ray bursts have occurred in the Milky Way's history. Most pointed harmlessly into intergalactic space. Some may have struck planets. We cannot know how many potential biospheres were sterilized before complex life could emerge. We cannot know if, elsewhere in the galaxy, civilizations more advanced than ours vanished in 83 seconds of gamma radiation arriving without warning at light speed. And gamma-ray bursts represent just one type of cosmic hazard. The universe contains structures and objects operating on even larger scales, wielding forces more subtle but equally inescapable. 330 million light-years from Earth, in the direction of the E constellation Boötes, there is a hole in reality, not a black hole, not a region where matter collapsed inward. A hole in the cosmic structure itself, a supervoid so vast and so empty that when Robert Kirshner and his team at the Harvard-Smithsonian Center for Astrophysics discovered it in 1981, they struggled to believe their data. They had been mapping galaxy positions, plotting the three-dimensional structure of the universe. The work was methodical, tedious. Measure the redshift of a galaxy to determine its distance. Record its position on the sky. Plot the point. Repeat thousands of times. And then, in one region, the points stopped appearing. The void they discovered spans 330 million light-years across. It contains approximately 60 galaxies. Statistical models of cosmic structure predict it should contain 2,000. The missing galaxies represent not a minor discrepancy, but a fundamental violation of how matter should distribute itself across the universe. Gravity pulls, dark matter clumps, galaxies form where dark matter concentrates. The cosmic web that astronomers observe across the universe shows this pattern clearly. Galaxies gather into clusters. Clusters link into filaments. Filaments surround voids. But the voids should be smaller. They should contain some galaxies. The Boötes void contains almost nothing. Imagine standing at the center of this emptiness. You exist on a planet orbiting a star in one of those 60 isolated galaxies. Your astronomers build telescopes, they survey the sky, and they find nothing. The nearest galaxy lies 150 million light-years away in any direction you look. Light from that galaxy began its journey before dinosaurs evolved on Earth. Your civilization develops cosmology. You measure the expansion rate. You calculate the universe's age. All your measurements are correct, but your fundamental assumption that the universe is filled with galaxies is wrong. You believe you are alone. You believe your galaxy is the entire universe, and you have no evidence suggesting otherwise. This isolation is not merely an observational limitation. It is an information horizon created by geometry. Light travels at a fixed speed. Look far enough away and you are looking backward in time. But the Botez void's emptiness extends across such distances that even looking billions of years into the past, you would see nothing. The void existed in this form when the light, now reaching its center, began its journey. A civilization inside would observe the cosmic microwave background radiation, that echo of the Big Bang visible from every point in the universe. They would measure its temperature at 2.7 Kelvin. They would detect the tiny fluctuations in that temperature that seeded galaxy formation. But looking outward, they would see no galaxies. The paradox would be inescapable. Scientists studying the Botez void have proposed several formation mechanisms, none entirely satisfactory. The most conventional explanation invokes quantum fluctuations in the infant universe. The Big Bang did not produce perfectly uniform density. Tiny variations existed, 1 part in 100,000. Denser regions pulled in more matter, grew denser still, eventually forming galaxies and galaxy clusters. Less dense regions lost matter to denser neighbors, becoming emptier. Over billions of years, this process created the cosmic web. The Botez void represents an extreme example, a region that started slightly less dense and lost most of its matter to surrounding structures. But the numbers do not quite work. Computer simulations of cosmic structure formation, seeded with observed density fluctuations from the cosmic microwave background, produce voids. They produce many voids. The universe is 30% galaxies and 70% voids by volume. This is expected, observed, normal. But the simulations struggle to produce voids as large and as empty as the Botez void without fine-tuning initial conditions. The void appears to be a statistical outlier, rare, perhaps unique. Or perhaps we simply have not surveyed enough volume to find others of comparable size. Alternative explanations venture into more speculative territory. Some cosmologists have suggested the void represents a region where dark energy density differs from the cosmic average. Dark energy, the mysterious force causing the universe's expansion to accelerate, comprises 70% of the universe's total energy density. We do not understand what it is. We observe its effects. We measure how it pushes space apart. But we do not know if its density is perfectly uniform. If dark energy density was slightly higher in some regions, those regions would expand faster, pushing matter away more efficiently, creating larger voids. The Botez void might mark a region where dark energy is winning more decisively than elsewhere. The void is not static. Measurements of galaxy velocities at its edges show they are moving away from the center. The void is expanding. As the universe expands, the voids expand faster than the clusters. Matter continues concentrating in filaments and clusters while the voids grow emptier. In 10 billion years, the Botez void will be larger. In 100 billion years, it will be enormous. Eventually, in the far future, as dark energy dominates completely, the universe will consist almost entirely of expanding voids with isolated galaxy clusters separated by distances light cannot cross in the age of the universe. The Botez void, offers a preview of the cosmos's final state. Other supervoids exist. The Eridanus supervoid, discovered through its effect on the cosmic microwave background, spans approximately 1 billion light-years. It is larger than the Boötes void, but less empty, containing thousands of galaxies rather than 60. The local void, much closer to the Milky Way at just 150 million light-years away, spans 60 million light-years across. We are not inside it, but we are near its edge. Our galaxy is part of the wall structure separating the local void from surrounding regions. If we lived inside the local void, our view of the universe would be dramatically different. We would see far fewer nearby galaxies. Our understanding of cosmology would have developed differently. The existence of the Boötes void raises a disturbing question about cosmic horror. We typically think of dangerous objects, black holes, magnetars, gamma-ray bursts, things that can kill through energy release. But the void represents a different kind of horror. The horror of absence, of emptiness so profound it challenges the assumption that the universe is filled with structure. A galaxy inside the Boötes void faces no immediate danger. No radiation will sterilize it. No black hole will consume it. But it exists alone, isolated, cut off from the rest of the cosmic community by distances so vast they might as well be infinite. Civilizations develop through exchange. Ideas spread between cultures. Technologies diffuse. On Earth, isolated civilizations developed differently from connected ones. Island populations evolved unique biology because they could not exchange genes with mainland populations. A galaxy inside the Boötes void is an island in an ocean 330 million light-years across. Even if that galaxy developed intelligent life, even if that life developed technology capable of interstellar travel, they would remain confined to their galaxy. The void is too large. The journey to the nearest galaxy would require 150 million years traveling at light speed. No civilization could maintain that journey. No technology could sustain it. From Earth's perspective, the Boötes void serves as a reminder that cosmic structure has limits. The universe is not uniformly filled with galaxies. Large regions exist where matter fled or never accumulated. We happen to live in a relatively dense region, part of the Laniakea supercluster, surrounded by other galaxies at distances close enough that we can observe them, study them, understand that we are not alone in the universe. But that situation is contingent, location dependent, a matter of cosmic geography. We are here, in this rich neighborhood of the cosmos, only because the quantum fluctuations that seeded structure 13.8 billion years ago happened to be denser here. The void is not the deadliest place in the universe. It is simply the loneliest. But loneliness on cosmic scales carries its own form of terror. The terror of existing in a universe that is fundamentally empty, where matter concentrates in rare pockets separated by unimaginable distances, where the default state is not stars and galaxies but void, where we are the exception, not the rule. The Boötes void is not where things die. It is where things never lived, where the universe simply said no to structure. And that absence, that emptiness, that 330 million light-year sphere of nothing is as terrifying as any object the cosmos contains. Yet compared to what lurks at the centers of galaxies, the void's passive horror seems almost gentle. At the center of the galaxy, NGC 1277, something impossible exists. The galaxy itself appears unremarkable from a distance. A lenticular galaxy, neither spiral nor elliptical, located 220 million light-years from Earth in the constellation Perseus. but buried at its core is a black hole that violates every model of how black holes should form. The object contains 17 billion solar masses. That mass alone is not unprecedented. Other supermassive black holes exceed it, but NGC 1277 is a small galaxy. The black hole comprises 14% of the galaxy's total stellar mass. That ratio is 10 times higher than any other known galaxy. It is as if the black hole formed first and the galaxy assembled itself around the monster as an afterthought. Supermassive black holes exist at the centers of most large galaxies. The Milky Way hosts Sagittarius A star, a 4 million solar mass black hole lurking 26,000 light-years from Earth. M87, the giant elliptical galaxy in the Virgo cluster, contains a black hole of 6.5 billion solar masses. These objects formed over billions of years, growing through accretion and mergers. Gas falls inward. Stars venture too close and are consumed. Smaller black holes merge with larger ones. Over cosmic time, the central black hole grows, but it grows in proportion to its galaxy. The relationship is consistent, predictable, until NGC 1277. The NGC 1277 black hole should not exist in its current form. The galaxy is not massive enough to have fed such a large black hole through normal accretion. The universe is not old enough for it to have grown this large through merger events alone. Something about its formation violated standard processes. Perhaps it formed from a direct collapse of a massive gas cloud in the early universe, bypassing the normal stellar evolution pathway. Perhaps it represents the merged remnant of multiple smaller black holes from a now disrupted cluster. Perhaps we simply do not understand how supermassive black holes form. The object exists. Our models struggle to explain it. TON 618, a quasar located 10.4 billion light-years from Earth, hosts an even more massive black hole. 66 billion solar masses concentrated in a region smaller than our solar system. The black hole's event horizon, the boundary beyond which nothing can escape, measures 11 times the distance from the Sun to Pluto. Light takes 14 hours to cross from one side of the event horizon to the other. This is not a black hole in the conventional sense. It is a cosmic abyss, a gravitational well so deep that material falling inward releases energy visible from across the observable universe. The energy release occurs in the accretion disk, the swirling maelstrom of gas and dust spiraling inward toward the event horizon. As material orbits closer to the black hole, it accelerates. Friction heats the gas. At distances just outside the event horizon, orbital velocities approach a significant fraction of light speed. The gas reaches temperatures exceeding 10 million degrees. At those temperatures, matter radiates in X-rays. The accretion disk around TON 618 shines with the luminosity of 140 trillion suns. That luminosity, emerging from a region just light hours across, makes TON 618 one of the brightest objects in the universe. M87 star, the black hole at the center of Messier 87, became the first black hole ever directly imaged when the Event Horizon Telescope collaboration released their observations in April of 2019. The image shows a dark circle surrounded by a glowing ring of emission. The dark circle is not the black hole itself, but its shadow, a region where photons cannot escape. The glowing ring is synchrotron radiation from relativistic electrons spiraling around magnetic field lines just outside the event horizon. The image is not high resolution by conventional standards. The black hole lies 53 million light-years away. But the Event Horizon Telescope, an Earth-sized array of radio telescopes operating in coordination, achieved angular resolution sufficient to image the event horizon's shadow. M87 star does not merely sit at the galaxy's center, it actively feeds. Material flows inward from the surrounding galaxy, but not all that material crosses the event horizon. Some is accelerated and expelled in jets shooting perpendicular to the accretion disk. These jets extend 5,000 light-years from the galaxy's core, moving at velocities exceeding 99% of light speed. The jets plow through intergalactic space, creating shock waves, heating gas, triggering star formation in their wake. They are visible across the electromagnetic spectrum, from radio waves to X-rays. They represent energy output on scales that dwarf anything stellar processes can produce. The jets emerge through a process that converts gravitational energy and rotational energy into directed kinetic energy. Material in the inner accretion disk orbits so close to the event horizon that it experiences frame dragging, the warping of spacetime by the black hole's rotation. The black hole spins, not slowly. Measurements suggest M87 star rotates at a significant fraction of the maximum rate allowed by general relativity. This rotation drags spacetime along with it, creating a region called the ergosphere where remaining stationary is impossible. Everything in the ergosphere must rotate with the black hole. This rotation stores energy. Magnetic fields threading the accretion disk can extract that energy, channeling it into jets. The most massive black hole currently known is Phoenix A, the central black hole in the Phoenix cluster, located 5.7 billion light-years from Earth. Mass estimates vary, but converge around 100 billion solar masses, 100 billion suns compressed into a region comparable in size to our solar system. The event horizon spans a diameter of 590 billion kilometers. Light takes 22 days to cross it. This is no longer a stellar mass object that collapsed. This is a galaxy mass object that somehow concentrated itself into a volume, tiny compared to the galaxy it inhabits. Black holes, this massive, create tidal forces that tear stars apart long before they reach the event horizon. A star approaching within a certain distance, called the tidal disruption radius, experiences differential gravitational forces stronger than the star's self-gravity. The side facing the black hole feels stronger pull than the far side. The star stretches, then ruptures. The stellar material streams toward the black hole in a process astronomers call spaghettification. The resulting debris forms a temporary accretion disk, flaring brightly as the disrupted star's material heats and radiates before crossing the event horizon. Telescopes detect these tidal disruption events as sudden brightening of previously quiet galactic cores. The danger a supermassive black hole poses depends entirely on distance. At the event horizon, escape is impossible. Physics forbids it. But the event horizon itself is small compared to galactic scales. Even for TON 618's 66 billion solar mass monster, the event horizon measures just light hours across. Stars orbiting 1 light-year away experience strong gravity but remain stable. Earth orbits Sagittarius A star at a distance of 26,000 light-years. At that distance, the black hole's gravitational influence is negligible compared to the collective gravity of all the stars in the galaxy. But proximity changes everything. Astronomers have discovered stars orbiting Sagittarius A star at distances measured in light hours. The star, designated S2, approaches within 17 light hours of the black hole at closest approach, completing an orbit every 16 years. Observations of S2's motion provided some of the strongest evidence for the black hole's existence and allowed precise measurement of its mass. S2 survives these close passes because it is a single, compact star. It is not being tidally disrupted, but a red giant star, larger and less gravitationally bound, would not survive such proximity. The supermassive black holes represent a different category of cosmic horror than magnetars or gamma-ray bursts. They do not strike suddenly. They do not release bursts of lethal radiation. They simply exist, massive beyond comprehension, pulling everything nearby inexorably inward. Their threat is patient, permanent. A star captured by a black hole's gravity may orbit for millions of years before spiraling close enough for disruption. But the outcome is inevitable. The orbit decays. Gravitational radiation carries away energy. The star falls closer, and eventually it crosses the tidal disruption radius. Then the event horizon. Then it is gone, its mass added to the black hole, increasing the monster's size by an infinitesimal amount. From outside, this process appears almost peaceful. No explosion marks a star's final moment. It simply dims as gravitational redshift stretches its light toward infrared wavelengths. Then it vanishes, crossed the event horizon. From the perspective of a distant observer, the star never quite reaches the event horizon. Time dilation means that as the star approaches, its clock slows relative to the outside universe. The final moments before crossing stretch toward infinity. But from the star's perspective, from the perspective of anything falling inward, the crossing occurs in finite time. And once crossed, there is no return, no escape, just the inexorable pull toward the singularity at the center, where space-time curvature becomes infinite and physics loses predictive power. These objects sit at galactic centers, anchoring the structures around them, governing the motions of billions of stars. They are not anomalies. They are fundamental components of galaxy formation and evolution. Nearly every large galaxy contains one. We orbit one. And while distance protects us now, the galaxy's future involves interactions that may not preserve that safety. But individual black holes, however massive, are not the only gravitational horrors the universe contains. 600 kilometers per second. That is how fast the Milky Way is moving towards something we cannot see. You are traveling at that velocity right now. The entire galaxy is traveling at that velocity. Our local group of galaxies, the Virgo supercluster, containing thousands of galaxy clusters, and everything within a region spanning hundreds of millions of light years, is being pulled toward a gravitational anomaly so massive that astronomers named it simply the Great Attractor. It lies 200 million light-years away in the direction of the constellation Triangulum Australe. And we cannot observe it directly because it hides behind the galactic plane, obscured by dust and stars of the Milky Way itself. The Great Attractor was discovered through motion, not observation. In the 1970s, astronomers mapping galaxy velocities noticed an anomaly. The universe is expanding. Galaxies recede from each other as space itself expands. But that recession is not perfectly uniform. Galaxies also move under the influence of gravity, pulled toward concentrations of mass. By measuring both the recession velocity from cosmic expansion and the peculiar velocity from gravitational attraction, astronomers can map the mass distribution in the universe. When they did this for galaxies in our cosmic neighborhood, they found everything moving toward a single point, a point hidden behind the zone of avoidance. The zone of avoidance is not a feature of the universe, but a limitation of observation. It is the region of sky blocked by our own galaxy. The Milky Way's disk, filled with dust and stars, absorbs visible light from objects behind it. Astronomers looking through the galactic plane, see foreground stars and gas but cannot detect distant galaxies. The zone of avoidance covers roughly 20% of the sky, and the Great Attractor lies directly behind it, hidden, detectable only through its gravitational influence on visible galaxies surrounding the obscured region. Estimates of the Great Attractor's mass vary, but converge around 10 to the 16 solar masses. That is tens of thousands of times the mass of the Milky Way. That mass is not concentrated in a single object, but spread across a region tens of millions of light years across. It is not a black hole. It is a massive concentration of galaxy clusters, an overdensity in the cosmic web so large it influences galactic motions across hundreds of millions of light years. We are falling toward it. We have been falling toward it for billions of years, and we will continue falling toward it for billions more. But the Great Attractor is not the full story. In the 1990s, astronomers discovered that the Great Attractor itself is moving. Galaxy velocity measurements extending to greater distances revealed a larger scale flow. The Great Attractor, the Virgo supercluster, the Hydra Centaurus supercluster, and everything within a sphere 500 million light-years across is moving toward an even more distant and more massive structure. This structure, lying approximately 600 million light-years away, is the Shapley supercluster. It contains more than 8,000 galaxies and represents one of the most massive structures in the observable universe. The Shapley supercluster pulls on our local region of space with gravitational force strong enough to affect galactic motions across 500 million light-years. It is not simply massive, it is the dominant mass concentration in our cosmic neighborhood. Everything within its sphere of influence is falling toward it, including us. Our motion toward the Great Attractor is partly motion toward the Shapley supercluster. We are being drawn into a gravitational well so deep and so broad that it governs the dynamics of thousands of galaxy clusters. Then, in 2008, astronomers announced the detection of something stranger: dark flow. Analysis of galaxy cluster motions using data from the Wilkinson Microwave Anisotropy Probe revealed that clusters across a vast region of the universe were moving in a coherent direction at velocities exceeding expectations. The motion was not toward the Great Attractor or the Shapley supercluster, but toward a point far beyond the observable universe's edge. The measured flow, velocity, exceeded 600 kilometers per second and extended across a region more than 3 billion light-years across. Dark flow, if confirmed, would suggest the existence of mass concentrations beyond the observable universe influencing structures we can see. The observable universe has a finite radius, approximately 46 billion light-years, determined by the distance light has traveled since the Big Bang. But the universe itself may be vastly larger, perhaps infinite. If massive structures exist beyond our observational horizon, their gravitational influence could still affect matter within the observable region. Dark flow might represent that influence, a pull toward mass we can never see because the light from those regions has not had time to reach us. The dark flow detection remains controversial. Subsequent analyses using different methods and datasets have produced conflicting results. Some studies confirm the flow, others find no evidence for it. The debate continues. But even the possibility that coherent motion on such scales exists raises disturbing questions about what lies beyond the edge of what we can observe. The observable universe may not be representative of the universe as a whole. We may inhabit a region with unusual properties, surrounded by structures we can never detect directly. The gravitational pull of the Great Attractor and Shapley supercluster creates no immediate danger. Galaxies do not collide catastrophically when they fall into massive clusters. They pass through, orbit, eventually settle into stable configurations. The Milky Way will not be destroyed by this motion, but it will be changed. Our trajectory through the cosmos is not random. It is determined by mass distributions on the largest scales. We are falling. We have always been falling. And where we end up depends on structures so massive and so distant we are only beginning to map them. This represents a different form of cosmic horror, not active threat, but passive inevitability. The universe is not static. It is dynamic. Everything moves. Everything falls towards something larger. Our galaxy, our local group, our supercluster, all are being pulled by gravitational forces we cannot resist. There is no escaping this motion, no way to alter course. We exist within a gravitational landscape shaped by structures billions of light years across, and that landscape determines where we go. The velocity of 600 kilometers per second sounds fast. It is more than 2 million kilometers per hour. Fast enough to cross from Earth to the Moon in less than 11 minutes. Fast enough to traverse the distance from the Sun to Neptune in just over 3 months. But on cosmic scales, it is slow. At this velocity, reaching the Great Attractor 200 million light-years away would require 330 billion years. The universe is only 13.8 billion years old. We will not reach the Great Attractor before the Sun exhausts. Its fuel expands into a red giant and consumes Earth. The motion is real. The pull is real. But the timescales are cosmological. Yet that timescale offers no comfort to the fundamental reality. We are not in control of our trajectory through the universe. Gravity dictates our motion. Mass concentrations we can barely observe determine where we go. And if structures beyond the observable universe exert influence through dark flow, then our destiny is shaped by things we can never see, never measure, never understand. We are passengers on a galactic ship falling through gravitational currents shaped by the universe's largest structures. And those currents are carrying us toward destinations determined billions of years ago by the distribution of matter in the infant cosmos. The Great Attractor and Shapley supercluster are not places in the conventional sense. They are not single objects, but vast regions of concentrated mass. They are destinations we approach not through choice, but through physics. And while they will not destroy us, they represent the inevitable reshaping of our cosmic environment. Galaxies drawn into massive clusters experience different evolution than isolated galaxies. Gas is stripped by interactions with hot intracluster medium. Star formation rates change. Morphology evolves. The Milky Way, falling into these structures over billions of years, will not remain unchanged. But while gravitational attraction pulls galaxies together, other objects wander alone, ejected from the structures that formed them. 70 to 170. That is how many rogue planets astronomers discovered in a single survey of the Upper Scorpius star-forming region, located 420 light-years from Earth. 70 to 170 planets wandering through interstellar space. No parent star, no solar system, just frozen worlds drifting alone through the void, ejected from their birth systems or formed in isolation, destined to travel through darkness for billions of years. And that survey covered just a tiny fraction of the galaxy. Extrapolate those numbers across the Milky Way's entire volume, and the implication becomes inescapable. Rogue planets may outnumber stars. Rogue planets form through two primary mechanisms. The first is ejection. In young planetary systems, gravitational interactions between forming planets can become violent. Large planets migrate inward or outward, their gravity perturbing smaller worlds. Sometimes these perturbations amplify. A planet receives a gravitational kick that increases its orbital eccentricity. The orbit becomes elliptical, then highly elliptical, then unbound. The planet reaches escape velocity and departs the system entirely, carrying only the velocity it gained from gravitational interactions. It becomes a rogue, a wanderer, an orphan cast out into interstellar space. The second mechanism bypasses planetary systems entirely. In dense star-forming regions, gas clouds can fragment into clumps too small to ignite fusion, but large enough to collapse into planet-sized objects. These objects never belonged to a star. They formed alone, condensing from the same molecular clouds that birth stars, but isolated, independent. They are planets by mass, but not by formation history. Astronomers debate whether to classify them as planets or sub-brown dwarfs. The distinction matters for taxonomy, but not for the objects themselves. They exist, they drift, they are alone. The Upper Scorpius survey used a technique called gravitational microlensing to detect these objects. Gravitational lensing occurs when a massive object passes between Earth and a background star. The foreground object's gravity bends light from the background star, briefly magnifying it. The magnification creates a characteristic light curve. The background star brightens, peaks, then dims as the lensing object moves past. The duration and shape of the light curve reveal the lensing object's mass. For rogue planets, those light curves last hours to days. Telescopes monitoring millions of stars can detect these brief events when a rogue planet crosses the line of sight to a background star. The detected rogue planets in Upper Scorpius range in mass from Jupiter-sized down to objects just a few times Earth's mass. The smaller the planet, the shorter the microlensing event, and the harder it is to detect. Current surveys are biased toward larger rogue planets. They miss Earth-sized rogues. Statistical models accounting for this detection bias suggest that for every Jupiter-mass rogue planet detected, 10 to 100 smaller rogues exist undetected. The galaxy may contain billions of Earth-sized rogue planets drifting unseen through interstellar space. A rogue planet's environment is hostile in ways different from stellar proximity hazards. There is no radiation bombardment, no stellar wind, no gamma-ray bursts, just cold. Absolute cold. Without a star to provide energy, a rogue planet's only heat sources are residual heat from formation and radioactive decay in its interior. For a Jupiter-sized gas giant, interior heat can maintain temperatures high enough that the upper atmosphere remains warmer than interstellar space. But for rocky planets like Earth, surface temperatures would plunge to near absolute zero. Oceans would freeze solid. Atmospheres would condense and fall as snow. The surface would become an icy wasteland, colder than the most extreme regions of our solar system. But beneath that frozen surface, conditions might differ. Radioactive decay in a planet's core releases heat. On Earth, radioactive decay of uranium, thorium, and potassium generates approximately 20 terawatts of power continuously. That heat drives plate tectonics, volcanic activity, and maintains the liquid outer core that generates Earth's magnetic field. A rogue Earth-sized planet would retain this internal heat source. The surface would freeze. But tens of kilometers down, temperatures could remain above freezing. Liquid water could exist in subsurface oceans, insulated by kilometers of ice, heated from below by radioactive decay and residual formation. Heat. Europa, Jupiter's moon, demonstrates this possibility within our own solar system. Europa's surface is frozen solid, a crust of water ice dozens of kilometers thick. But beneath that crust lies a subsurface ocean containing more liquid water than all of Earth's oceans combined. The ocean exists not because of sunlight, which is too weak at Jupiter's distance to melt ice, but because of tidal heating from Jupiter's gravity and radioactive decay in Europa's interior. A rogue planet needs no parent star to maintain subsurface liquid water. It needs only sufficient mass to retain internal heat. This raises an unsettling possibility. Life may exist on rogue planets, not on the frozen surface, but in the dark oceans beneath. Life that evolved without sunlight. Life powered by chemical energy from hydrothermal vents, similar to the ecosystems at Earth's ocean floor. These ecosystems exist independently of photosynthesis. They derive energy from the chemical reactions between seawater and minerals at vent sites. Bacteria oxidize hydrogen sulfide. Larger organisms consume the bacteria. Complex food webs emerge in absolute darkness. On Earth, these ecosystems are secondary. They evolved in an ocean dominated by photosynthetic organisms. But on a rogue planet, chemosynthetic life could be primary, the only life, existing in darkness, alone. The longevity of such life depends on the heat source. Radioactive decay rates are fixed by nuclear physics. Uranium-238 has a half-life of 4.5 billion years. Thorium-232's half-life is 14 billion years. A rogue planet's internal heat diminishes over time, but persists for billions of years. Long enough for life to originate, evolve, diversify. Long enough for complex ecosystems to develop, but not forever. Eventually, the radioactive isotopes decay away. Heat production drops. The subsurface ocean freezes from the bottom up. The ecosystem shrinks, then dies. Extinction imposed not by cosmic catastrophe, but by thermodynamics. The wandering trajectory of a rogue planet is essentially random. Ejected from a planetary system, the planet inherits some orbital velocity around the galaxy, but loses its connection to a specific star. It drifts through the galactic disk, passing through molecular clouds, traversing spiral arms, occasionally passing near star systems, but almost never close enough to be captured. The gravitational cross-section for capture is small. A rogue planet would need to pass within a specific distance range of a star with precisely the right relative velocity to be captured into orbit. The probability of this occurring is negligible. Most rogue planets will wander alone for the galaxy's entire lifetime. Current estimates suggest there may be 2 billion rogue planets in the Milky Way. Some estimates go higher, perhaps 10 billion, perhaps 100 billion. Perhaps more planets wander alone than orbit stars. This transforms our understanding of planetary demographics. Planets are not rare, they are common, but most exist in darkness, frozen, alone, untethered to stars. And if even a small fraction harbor subsurface oceans, then the galaxy may contain billions of isolated biospheres, each evolving independently, each unaware that anything exists beyond their frozen world. The horror of the rogue planet is not violence, but isolation. It is existence without context, a world that will never see a star, never feel sunlight, never be part of a solar system. A planet drifting through space for billions of years, its trajectory determined by the gravitational kick that ejected it, its fate sealed. No rescue, no capture, no change, just motion through the void. And if life exists there, it exists in the ultimate isolation, trapped beneath kilometers of ice on a world that will never encounter another inhabited planet, never communicate, never know it is not alone. These wandering worlds experience no active danger, but they represent a fate perhaps worse than destruction. They represent permanent exile, and scattered throughout our galaxy are billions of them, invisible, undetected, drifting forever through the darkness between stars. But while rogue planets drift passively, other objects actively destroy everything that approaches them. There is a boundary in space-time where the rules change completely. Cross it and you can never return, not because you lack fuel, not because you lack speed, but because the geometry of space-time itself forbids backward motion. This boundary is the event horizon. It surrounds every black hole. And what happens at and beyond that boundary represents physics at its most extreme. At the event horizon of Sagittarius A star, the 4 million solar mass black hole at our galaxy's center, the escape velocity equals the speed of light. That is the definition. The event horizon marks the distance from the singularity where escape requires light speed. Inside that radius, escape requires exceeding light speed. Physics forbids it. You are trapped. The Schwarzschild radius defines the event horizon's location for a non-rotating black hole. The formula is simple. The radius equals 2 times the gravitational constant times the mass divided by the speed of light squared. For a black hole with 1 solar mass, the Schwarzschild radius measures 3 kilometers. Double the mass, double the radius. A 4 million solar mass black hole, like Sagittarius A star, has a Schwarzschild radius of 12 million kilometers. That is approximately 17 times the radius of the Sun. The entire black hole, the region from which nothing can escape, fits inside a sphere smaller than Mercury's orbit. But most black holes rotate. Rotation changes the geometry. A rotating black hole drags space-time around with it, creating a region outside the event horizon called the ergosphere. In the ergosphere, remaining stationary is impossible. Space-time itself rotates. You must rotate with it. The event horizon of a rotating black hole is not spherical but oblate, compressed along the rotation axis. For a maximally rotating black hole, one spinning at the theoretical maximum rate allowed by general relativity, the event horizon radius at the equator is half the Schwarzschild radius. The black hole becomes smaller as it spins faster, more compact, more extreme. Approach a black hole from a safe distance and you experience normal gravity. Newtonian mechanics applies. The gravitational force decreases with the square of distance. Orbit at a stable radius. Accelerate away if you choose. Nothing unusual happens. But as you approach closer, relativistic effects emerge. Time dilation becomes measurable. Your clock runs slower relative to distant observers. Gravitational redshift lengthens wavelengths of light you emit outward. These effects strengthen as you approach. At the event horizon, time dilation becomes infinite. From the perspective of a distant observer, your clock stops. You freeze at the horizon, never quite crossing, your image redshifting into invisibility. But from your perspective, crossing occurs in finite time. You fall inward. The event horizon is not a physical barrier. No wall exists, no membrane. Nothing marks the location except geometry. You cross without noticing. One moment you are outside, capable of escape. The next moment you are inside, and escape has become impossible. The transition is smooth, continuous, but irreversible. Behind you, the universe continues. Ahead lies only the singularity. Space-time curvature inside the event horizon becomes so extreme that all future-directed paths point inward. Outward is no longer a direction you can travel. It is a direction in time, specifically the past. The singularity at the black hole's center is not a place in the conventional sense. It is a moment in your future that you cannot avoid. General relativity predicts that space-time curvature becomes infinite at the singularity. Density becomes infinite. Tidal forces become infinite. Matter cannot survive. You are compressed, stretched, torn apart at the atomic level, then subatomic, then beyond. The mathematics breaks down. Infinity appears in the equations. Physics loses predictive power. What actually happens at the singularity is unknown because general relativity, the theory that describes black holes, fails when curvature becomes infinite. Before reaching the singularity, tidal forces destroy you. Tidal forces arise from the difference in gravitational strength across a finite distance. Your feet, closer to the singularity than your head, experience stronger gravity. The difference creates a stretching force. For a stellar mass black hole, those tidal forces become lethal far outside the event horizon. A 10 solar mass black hole has an event horizon radius of 30 kilometers. But the tidal forces at that distance would already have torn a human body apart. You would be spaghettified long before crossing the horizon, stretched into a stream of atoms, then compressed laterally as the geometry squeezes matter toward the singularity. Supermassive black holes present a different scenario. Their event horizons are enormous. TON 618's event horizon measures 11 times the distance from the Sun to Pluto. Tidal forces at that distance are comparatively mild. A human could cross the event horizon of a supermassive black hole and survive. Briefly, the tidal forces increase as you fall inward, but for several seconds, perhaps minutes, you would remain intact, conscious, aware that you have crossed a boundary from which no return is possible, aware that ahead lies only the singularity and annihilation. The accretion disk surrounding an active black hole creates hazards distinct from the black hole itself. Material spiraling inward releases gravitational potential energy as heat. The inner regions of the accretion disk reach temperatures exceeding 10 million degrees. At those temperatures, matter radiates X-rays. Approach the disk and you are bathed in lethal radiation long before approaching the event horizon. The radiation environment near an actively feeding black hole would kill you in seconds. Ionizing radiation destroys molecular bonds. Cells die. DNA shatters. No biological organism could survive proximity to an active accretion disk. Some black holes launch jets. M87 star's jets extend 5,000 light-years from the galaxy's core. Material in these jets moves at 99% of light speed. The jets are particle beams, electrons and positrons accelerated to relativistic energies by magnetic fields in the ergosphere. The energy density in the jets is catastrophic. They plow through intergalactic space, creating shock waves, heating gas to millions of degrees. If you were caught in such a jet, you would be vaporized instantly. Atoms would be ionized, stripped of electrons, reduced to plasma. Then, that plasma would be accelerated to near light speed and expelled into intergalactic space. Black hole mergers represent the most violent events the universe produces outside of the Big Bang itself. When two black holes orbit each other, they radiate gravitational waves. Those waves carry away energy and angular momentum. The orbit decays. The black holes spiral closer. Eventually, they merge. The merger lasts milliseconds. During those milliseconds, the collision releases more power than all the stars in the observable universe combined. That power emerges not as light or matter, but as gravitational radiation. Ripples in spacetime, propagating outward at light speed. The first gravitational wave detection by LIGO in September 2015 captured the merger of two black holes 36 and 29 solar masses located 1.3 billion light-years from Earth. The region surrounding a merging black hole pair is lethal across vast distances. The gravitational waves themselves do not directly threaten distant observers. They are weak by the time they reach us. But close to the merger, gravitational wave amplitudes become extreme. Space-time oscillates, stretches, compresses. Any object near the merger would be subjected to tidal forces that vary at frequencies of hundreds of hertz. The object would be rhythmically stretched and compressed, torn apart, reassembled, torn apart again. The violence would continue until the merger completed and the new, larger black hole settled into equilibrium. Black holes are not rare. The Milky Way contains approximately 100 million stellar mass black holes, remnants of massive stars that exhausted their fuel and collapsed. Most are invisible, isolated, not actively accreting material. They drift through the galaxy, dark, detectable only through gravitational effects on nearby objects. Occasionally, one passes close to a star. The star is disrupted. The black hole feeds. A flare of X-rays marks the event. Then, the black hole fades back into invisibility. These encounters are random, unpredictable. A black hole could pass through the solar system. The probability is low, but non-zero. If a stellar mass black hole passed through the solar system, the effects would depend on trajectory and distance. A distant passage, several astronomical units from the Sun, would perturb planetary orbits but cause no immediate catastrophe. A close passage, within 1 astronomical unit, would gravitationally disrupt planets. Earth's orbit would change. We could be ejected from the solar system, turned into a rogue planet. Or our orbit could become highly eccentric, plunging us into the Sun or sending us into the outer solar system where temperatures drop below the freezing point of carbon dioxide. Either outcome means the end of the biosphere, but the most likely scenario is no passage at all. Space is vast, black holes are small. The cross-section for a black hole to pass close to any given star is negligible. The Milky Way has existed for 13 billion years. It contains 100 million stellar mass black holes and 400 billion stars. Encounters occur, but they are rare. We have no evidence any black hole has ever passed near the Sun. We have no reason to expect one will. The threat is theoretical, present, but statistically unlikely. The event horizon represents the ultimate point of no return. A boundary defined not by matter or energy, but by geometry. And beyond that boundary lies a region we can describe mathematically, but cannot observe, cannot visit and return, cannot probe with instruments. What happens beyond the event horizon is inference, theory, mathematics, not observation. The event horizon is the edge of the knowable universe, and millions of these edges exist within our galaxy alone. Yet black holes are not the only objects that warp reality, itself through extreme physics, 100 trillion times stronger than Earth's magnetic field. That is the force SGR 0501 plus 4516 wields as it races through the galaxy. But magnetic fields alone do not tell the complete story of extreme radiation environments. Around certain cosmic objects, radiation reaches intensities that make the term lethal seem inadequate. These are not places where you would die quickly. These are places where matter itself cannot maintain structural integrity, where atoms are ionized, where molecular bonds shatter, where the electromagnetic environment is so violent that the distinction between solid, liquid, and gas becomes meaningless. everything becomes plasma. Quasars represent the most luminous persistent objects in the universe. They are supermassive black holes actively feeding, consuming material at rates exceeding 1 solar mass per year. The accretion disk around a bright quasar releases energy equivalent to 1 trillion suns. That energy emerges across the electromagnetic spectrum. Radio waves, infrared, visible light, ultraviolet, X-rays, gamma rays. The quasar 3C273, located 2.4 billion light-years from Earth, outputs a luminosity of 4 times 10 to the 40th watts. For comparison, the Sun's total luminosity is 4 times 10 to the 26th watts. The quasar is 100 trillion times more luminous, and that luminosity emerges from a region smaller than our solar system. Approach within 1 light-year of an active quasar, and the radiation environment becomes incompatible with matter as we know it. The photon flux at that distance exceeds 10 to the 20th photons per square centimeter per second. Those photons span all energies. Many are X-rays and gamma rays, carrying enough energy to ionize atoms through Compton scattering. An atom struck by such a photon loses electrons. The atom becomes an ion. Then another photon strikes. Then another. The bombardment is continuous, relentless. There is no recovery time, no pause. The radiation field is so intense that neutral atoms cannot exist. Everything is plasma. The magnetic fields threading quasar accretion disks amplify the danger. These fields measure thousands of Gauss at distances comparable to the event horizon. That strength is sufficient to channel particle motion. Electrons and positrons spiral along field lines, accelerating to relativistic velocities. As they accelerate, they radiate synchrotron emission. This is the mechanism producing the bright radiation we observe from quasars. But for an object caught in that environment, the accelerating particles represent a particle beam. A stream of relativistic electrons striking matter at energies exceeding 1 trillion electron volts. Each impact creates a cascade. Secondary particles, more radiation, the target heats, vaporizes, ionizes. Magnetar radiation environments operate through different mechanisms but achieve comparable violence. When a magnetar experiences a starquake, the crust cracks. Magnetic field lines snap and reconnect. The reconnection releases energy stored in the magnetic field. That energy emerges as X-rays and gamma rays. The December 2004 burst from SGR 1806-20 released 10 to the 46 joules in 1/10 of a second. That is more energy than the Sun produces in 150,000 years, released in the time it takes you to blink. The burst propagated outward as a spherical shell of gamma radiation traveling at light speed. At a distance of 1,000 kilometers from a magnetar's surface during such a burst, the gamma ray flux would exceed 10 to the 25 photons per square centimeter per second. Each photon carries energy measured in millions of electron volts. The total energy flux would vaporize any material object instantly. Rock, metal, carbon composites, biological tissue. None would survive. The gamma rays would penetrate matter, depositing energy through Compton, scattering, and pair production. The material would heat to millions of degrees in microseconds. The thermal energy would exceed the binding energy holding atoms in molecular structures. The object would explode. Not metaphorically, literally. Every component atom would gain enough kinetic energy to overcome all binding forces and disperse. But magnetars also produce persistent radiation between bursts. Their magnetic fields decay continuously, releasing a steady flux of X-rays. SGR 0, 50, 1 plus 4516 emits X-rays with luminosities of approximately 10 to the 35 ergs per second. That is 10,000 times the Sun's total luminosity, emerging entirely as high-energy X-rays from an object 20 kilometers across. The X-ray flux at a distance of 1,000 kilometers exceeds 10 to the 15 ergs per square centimeter per second. For comparison, the X-ray flux from the Sun at Earth's orbit is 10 to the minus 2 ergs per square centimeter per second. The magnetar's X-ray environment is 10,000 trillion times more intense. Neutron star surfaces present radiation environments coupled with gravitational extremes. Surface temperatures on young neutron stars exceed 1 million degrees. At those temperatures, matter radiates in X-rays. The surface gravity, 200 billion times Earth's gravity, compresses the atmosphere into a layer less than 1 centimeter thick. That atmosphere is not composed of ordinary atoms, but of iron ions and free electrons, held in a state of partial ionization by the intense radiation field. Land on such a surface and you would not stand. You would be compressed into a layer of degenerate matter thinner than a sheet of paper. Simultaneously, the radiation field would ionize every atom in your body. You would cease to exist as organized matter. Pulsar wind nebulae create radiation environments distributed across larger volumes. The Crab Nebula, remnant of a supernova observed in 1054 CE, contains a pulsar rotating 30 times per second. That rotation drives a wind of relativistic particles outward into the surrounding nebula. The particles interact with magnetic fields, producing synchrotron radiation across the electromagnetic spectrum. The total energy output exceeds 100,000 solar luminosities. The nebula glows not from thermal emission, but from particles accelerated to nearly light speed, radiating as they spiral around magnetic field lines. Within the Crab Nebula, radiation levels vary with distance from the central pulsar. Near the pulsar, within light seconds of the neutron star, the environment resembles conditions near a magnetar. Particle energies exceed 1 trillion electron volts. The radiation field ionizes all matter, but farther out, at distances measured in light years, the environment becomes merely hostile rather than instantly lethal. You would still die from radiation exposure, but death would take hours rather than microseconds. The distinction is meaningful only in principle. Both environments are absolutely incompatible with life. The jets emerging from active galactic nuclei create linear radiation environments extending thousands of light years. M87's jet, visible in radio and optical wavelengths, contains electrons moving at 99.99% of light speed. The jet's magnetic field strength measures microgauss, weak by terrestrial standards but significant when coupled with relativistic particle densities. The synchrotron radiation from the jet produces a radiation field lethal across distances measured in astronomical units. Approach within 1 AU of the jet and you enter a particle beam. The electrons would penetrate any shielding. They would deposit energy through ionization and Bremsstrahlung radiation. The target would heat, then vaporize, then ionize. These radiation environments share a common feature. They are not merely intense, they are sustained. A gamma-ray burst lasts seconds. Its danger is brief, assuming you survive. But quasars shine for millions of years. Magnetars radiate for thousands of years. Pulsar winds persist for tens of thousands of years. These are not transient hazards, but permanent features of the cosmic landscape. Regions where the radiation environment prohibits the existence of complex structures, where chemistry cannot occur because molecular bonds cannot form, where life is not merely impossible, but conceptually meaningless. The horror of these environments is their persistence. A magnetar will radiate X-rays for 10,000 years as its magnetic field decays. During that entire period, the region within light seconds of the magnetar remains sterilized. Nothing can approach. Nothing can survive. The magnetar creates a sphere of death, light seconds across, maintained continuously for millennia, and scattered through the galaxy are millions of neutron stars, some active magnetars, others quiescent pulsars, each surrounded by radiation environments hostile to matter itself. Earth exists in a comparatively gentle radiation environment. The sun emits across the spectrum, but most energy emerges as visible light. Our atmosphere absorbs ultraviolet and X-rays. The magnetosphere deflects charged particles. We live in a protected bubble, but that bubble is contingent, temporary. Located far from any extreme radiation source purely by chance. 1 light year closer to a magnetar would mean no Earth, no solar system, no possibility of planets forming in an environment where radiation prevents molecular clouds from collapsing into stars. Yet radiation represents only one category of environmental hazard. The universe also contains regions defined not by what they contain, but by what they lack. 80%. That is the fraction of the observable universe's volume occupied by cosmic voids. Not space between stars within galaxies, not space between galaxies within clusters, but supervoids. Regions hundreds of millions of light years across, containing almost no galaxies, almost no matter, almost nothing. The cosmic web we observe when we map large-scale structure consists of filaments and clusters separated by enormous empty regions. And those empty regions dominate. Matter concentrates in walls and filaments comprising 20% of the volume. The remaining 80% is void. The universe is mostly emptiness. Matter is the exception, not the rule. The Bhuta's void, spanning 330 million light-years, represents the largest and emptiest known supervoid, but it is not alone. The Eridanus supervoid, centered approximately 1 billion light-years from Earth, spans approximately 1 billion light-years across. It is larger than the Bhuta's void, but less empty, containing thousands of galaxies rather than 60. The void's existence was inferred from its effect on the cosmic microwave background radiation. Photons from the CMB traveling through the void experience a temperature shift due to the integrated Sachs-Wolf effect. The void appears as a cold spot in CMB maps, a region where the temperature is lower than surrounding areas by several tens of microkelvins. The local void lies much closer, just 150 million light-years from the Milky Way. It spans approximately 60 million light-years and contains fewer than 100 galaxies. Our galaxy sits at the edge of this void, part of the wall structure separating the local void from denser regions beyond. If we were located inside the local void rather than at its edge, our view of the universe would be profoundly different. Looking outward, we would see far fewer nearby galaxies. The Andromeda Galaxy, currently 2.5 million light-years away, would still be visible, but most other galaxies in our local environment would be absent. The void would extend around us in every direction. Imagine existing inside a supervoid, your galaxy formed in a region of slightly lower than average density. Surrounding galaxies were farther away than typical. As the universe expanded, those galaxies receded. The void grew. Now, billions of years later, you look outward with telescopes and see almost nothing. The nearest galaxy lies 100 million light-years away. The next nearest is 200 million light-years distant. Your galaxy is an island, isolated, cut off from the cosmic community by distances so vast they are effectively infinite. Your astronomers would still detect the cosmic microwave background radiation. They would measure the Hubble constant describing cosmic expansion. They would calculate the universe's age at 13.8 billion years. All the cosmological parameters would be correct, but their observational sample would be limited. Measuring galaxy clustering patterns requires observing many galaxies. Detecting the cosmic web requires mapping structure across large volumes. Inside a supervoid, the data would be sparse. Understanding that the universe elsewhere is filled with galaxies would require theoretical inference, not direct observation. The environment inside a supervoid is not hostile. There is no increased radiation, no gravitational anomalies, just absence. The galaxy density is lower. Star formation rates in void galaxies tend to be slightly suppressed compared to galaxies in denser environments because gas, accretion from the intergalactic medium, is reduced. But stars still form, planets still orbit those stars. Life could emerge, civilizations could develop. They would simply do so in profound isolation. The dynamics of void expansion differ from cosmic expansion in denser regions. Voids expand faster than average. The low density means less gravitational deceleration. Dark energy, the force driving cosmic expansion to accelerate, dominates more completely in voids because there is less matter to resist it. Measurements of void expansion rates show they grow approximately 30% faster than regions of average density. This means voids become emptier over time. Galaxies at void edges accelerate away from the center. The void expands, and as it expands, the isolation of any galaxy within it deepens. In the far future, as dark energy continues to drive accelerating expansion, the voids will dominate completely. Galaxy clusters will remain gravitationally bound, but the space between clusters will expand without limit. Eventually, clusters will become isolated. No light from other clusters will reach them because the space between expands faster than light can cross it. Each cluster will become a cosmic island, an isolated structure surrounded by void, expanding to infinity. This is the universe's far future. Not collapse, not heat death in the traditional sense, but isolation. Infinite expansion, creating infinite distance between all gravitationally unbound structures. The Eridanus supervoid's effect on the cosmic microwave background demonstrates how voids influence even the oldest light in the universe. Photons from the CMB, traveling through the void, experience a gravitational blue shift as they fall into the void's gravitational potential. Then they experience a red shift as they climb back out. If the void were static, these effects would cancel. But the void is expanding. The red shift when exiting is slightly smaller than the blue shift when entering, because the void's gravitational potential has weakened due to expansion. The net result is a slight cooling of the photons. They arrive at our telescopes with temperatures lower than photons that traveled through denser regions. This effect allows astronomers to map voids using CMB data. The Planck satellite, which mapped the CMB with unprecedented precision, revealed numerous cold spots corresponding to supervoids along the line of sight. Each cold spot marks a region where photons traveled through lower than average density. The largest of these spots, the CMB cold spot in the constellation Eridanus, has been attributed to the Eridanus supervoid. But some researchers argue the void alone cannot fully explain the spot's amplitude. They suggest additional explanations, perhaps multiple voids along the line of sight, perhaps a statistical fluctuation, perhaps something stranger. The psychological impact of void environments on hypothetical civilizations is speculative but worth considering. Humans developed astronomy by observing thousands of stars with naked eyes. Early civilizations mapped constellations, tracked planetary motions, built cosmological models. Our understanding of the universe emerged from observing a rich night sky. But a civilization inside a supervoid would observe a sparse sky, fewer stars in their galaxy due to suppressed star formation, no nearby galaxies, just darkness. Would such a civilization develop astronomy? Would they invest resources in building telescopes to study a sky that appears mostly empty? Perhaps they would conclude they were alone. Perhaps they would assume their galaxy was the entire universe. Without nearby galaxies to observe, detecting cosmic expansion would be harder. Measuring the Hubble constant requires observing galaxies at various distances and measuring their recession velocities. With only distant galaxies available, the measurements become more difficult, more uncertain. The civilization might conclude the universe is static, unchanging. They would be wrong, but their observational evidence would be limited. Or perhaps they would be more motivated to explore. Perhaps the emptiness would drive them to build more powerful telescopes, to search harder for any sign they are not alone. Perhaps they would eventually detect the distant galaxies hundreds of millions of light years away and realize they inhabit an unusually empty region. They would understand they are isolated not because they are unique, but because they exist in a statistical outlier, a region that, through quantum fluctuations in the infant universe, started slightly less dense and evolved into a vast void. Either way, their experience of the universe would differ fundamentally from ours. We live in a rich environment, part of a galaxy cluster, surrounded by observable galaxies at distances close enough that we can study them in detail. We can see structure, we can map the cosmic web, we can understand our place within it. A civilization inside a supervoid lacks that context. They exist in emptiness, and while that emptiness does not threaten their survival, it shapes their understanding of reality itself. The voids represent cosmic horror through absence rather than presence. They are not dangerous, they are empty. But that emptiness, stretched across hundreds of millions of light years, creates isolation so complete it becomes existentially significant. You are not threatened. You are alone. And in a universe where connection and communication define meaning, isolation on such scales might be worse than annihilation. But some cosmic objects combine emptiness with violence in ways that defy comprehension. 1 teaspoon of neutron star material weighs 1 billion tons. That is not an approximation. That is the actual density of degenerate neutron matter, compressed under gravitational forces so extreme that atomic structure collapses. Electrons merge with protons, forming neutrons. Those neutrons pack together until they touch. No space remains between particles. The density reaches 400 trillion grams per cubic centimeter. A sugar cube of this matter weighs as much as all of humanity. A teaspoon weighs more than Mount Everest, and an entire neutron star, containing more mass than the Sun, occupies a sphere just 20 kilometers across. Neutron stars form when massive stars exhaust their nuclear fuel and collapse. The collapse occurs in less than 1 second. The star's iron core, previously supported by fusion energy, loses that support. Electron degeneracy pressure provides brief resistance but proves insufficient. The core collapses. Electrons merge with protons in a process called electron capture. Neutrons remain. The collapse continues until neutron degeneracy pressure, a quantum mechanical effect arising from the Pauli exclusion principle, finally halts it. The core rebounds. The outer layers, still falling inward, collide with the rebounding core. The collision produces a shockwave. The shockwave propagates outward. The star explodes, a supernova, and at the center, a neutron star remains. The surface gravity on a neutron star exceeds 200 billion times Earth's gravity. If you could somehow place a marshmallow on a neutron star's surface, ignoring the radiation and magnetic fields that would destroy it long before arrival, that marshmallow would weigh as much as the Great Pyramid of Giza. The gravitational acceleration at the surface measures 2 × 10 to the 14th centimeters per second squared. Drop a knee object from 1 meter above the surface, and it would impact at nearly half the speed of light. The kinetic energy released on impact would exceed the energy of a nuclear weapon. But you cannot place anything on a neutron star's surface gently. Approach from space and gravity accelerates you continuously. By the time you reach the surface, your velocity would exceed significant fractions of light speed. The impact would convert your kinetic energy to thermal energy instantly. You would not splatter. You would vaporize, then ionize. Then the ions would be compressed into the neutron star's crust, adding an infinitesimal amount of mass to the object. The crust itself consists of neutron-rich nuclei arranged in a crystalline lattice. At shallow depths, the nuclei resemble ordinary heavy elements, but with extreme neutron excess. Deeper down, the nuclei become exotic. Nuclear pasta. Physicists use this term seriously to describe the shapes nuclei assume under extreme pressure. Gnocchi phase, spaghetti phase, lasagna phase. These names refer to rod-like, sheet-like, and tubular nuclear structures predicted by theoretical models. The crust extends down approximately 1 kilometer before giving way to the core. The core contains matter at densities exceeding nuclear density. What exactly that matter is remains uncertain. At the lower end of the density range, neutrons dominate with a small fraction of protons and electrons to maintain charge neutrality. At higher densities, hyperons might appear. Strange quarks might become unconfined, forming quark matter. The core of the most massive neutron stars might be composed entirely of quark-gluon plasma. We do not know. The physics of matter at these densities cannot be replicated in laboratories. We must infer from observations and extrapolate from theory, but the observations are limited and the theory is uncertain. Pulsars are rotating neutron stars with strong magnetic fields aligned at angles to their rotation axes. As the neutron star rotates, the magnetic field rotates with it. Charged particles near the magnetic poles are accelerated along field lines, producing beams of radiation. Those beams sweep across space like lighthouse beams. If Earth lies in the path of a beam, we detect a pulse each rotation. The Crab pulsar rotates 30 times per second. Each rotation brings the beam across Earth. We detect 30 pulses per second. The pulsar has maintained this rate, slowly decreasing, since its formation in 1054 CE, when Chinese astronomers recorded the supernova that created it. The rotation rate decreases because the pulsar loses energy. Rotating magnetic fields radiate electromagnetic energy. The radiation carries away angular momentum. The pulsar slows down. The Crab pulsar's rotation period increases by 38 nanoseconds per day. That sounds negligible, but over centuries, the deceleration accumulates. Eventually, in approximately tens of thousands of years, the Crab pulsar will slow to the point where the radiation mechanism shuts off. It will cease being a pulsar. It will become a quiet neutron star, still rotating but no longer producing detectable beams. Millisecond pulsars rotate much faster, hundreds of times per second. The fastest known pulsar, PSRJ 1748-2446 AD, rotates 716 times per second. 716 rotations every second means the surface of this 20-kilometer object moves at approximately 20% of light speed. The centrifugal force nearly tears the neutron star apart. Only gravity holds it together. If the rotation rate increased much further, the neutron star would exceed its stability limit and disintegrate. This represents the fastest rotation rate possible for an object of this mass and radius. Millisecond pulsars achieve their high rotation rates through accretion. They exist in binary systems with companion stars. Material from the companion falls onto the neutron star. As it spirals inward, it carries angular momentum. That angular momentum transfers to the neutron star, spinning it up. Over millions of years, the neutron star accelerates from a rotation period of seconds to milliseconds. The process is called recycling. The neutron star, previously slowed by magnetic braking, is spun up again by accreted material. When the accretion stops, the neutron star continues rotating at its newly acquired high rate. Some neutron stars consume their companions entirely. The process takes millions of years, but the outcome is certain. The companion star loses mass to the neutron star. The companion shrinks. Eventually, it is completely consumed. The neutron star, now slightly more massive and rapidly rotating, is left alone. These are the isolated millisecond pulsars. They rotate hundreds of times per second, but have no companion. The companion was destroyed, consumed, converted into additional neutron star mass and rotational energy. Black widow pulsars take this process to an extreme. They are neutron stars in binary systems where the pulsar's radiation is actively destroying the companion. The pulsar wind, a stream of relativistic particles, strikes the companion star. The radiation heats the companion's surface. Material evaporates. The evaporated material forms a cloud around the system. That cloud is visible in optical wavelengths, glowing from the energy deposited by the pulsar's radiation. The companion is being eaten alive, slowly, over millions of years. Eventually, the companion will be reduced to nothing. The Black Widow pulsar will have consumed it completely. Neutron stars in binary systems can merge. When two neutron stars orbit each other, they radiate gravitational waves. Those waves carry away energy and angular momentum. The orbit decays, the neutron stars spiral closer. Eventually, they collide. The collision produces either a more massive neutron star or a black hole, depending on the total mass. The merger also produces a kilonova, an explosion powered by radioactive decay of heavy elements synthesized during the merger. The August 2017 detection of gravitational waves from a neutron star merger, followed by observations of the kilonovias across the electromagnetic spectrum, confirmed that neutron star mergers are primary sites of heavy element production in the universe. The tidal forces during a neutron star merger are incomprehensible. As the two neutron stars approach within kilometers of each other, each experiences tidal distortion from the other's gravity. The neutron stars stretch, deform, their crusts crack. Matter is ejected into space. The ejected material, rich in neutrons, undergoes rapid neutron capture, synthesizing elements heavier than iron: gold, platinum, uranium. All the heaviest elements in the universe were created in neutron star mergers and supernova explosions. The gold in jewelry, the uranium in nuclear reactors, all of it was synthesized in events like this. events of unimaginable violence occurring when dead stars collide. Neutron stars represent an intermediate state, more massive than white dwarfs, but less massive than black holes. The Tolman-Oppenheimer-Volkoff limit defines the maximum mass a neutron star can have before collapsing into a black hole. That limit depends on the equation of state of neutron matter, which is uncertain. Current estimates place it between 2 and 3 solar masses. A neutron star more massive than this limit cannot be supported by neutron degeneracy pressure. It collapses. An event horizon forms. The neutron star becomes a black hole. The transition is inevitable for sufficiently massive neutron stars. But before that transition occurs, the neutron star exists in a state that defies intuition. A sphere 20 kilometers across, containing more mass than the Sun. A surface gravity sufficient to compress atoms into neutronium. Magnetic fields strong enough to distort quantum vacuum. Rotation rates approaching relativistic speeds at the equator. These are not merely extreme objects. They are objects operating at the absolute edge of what physics allows. One step further and they cross into black hole territory. But at this boundary, they persist, spinning, radiating, slowly dying. And some of them, the magnetars, combine all these extremes with magnetic fields so powerful they represent a category of cosmic horror entirely their own. 1.3 billion light-years from Earth, on September 14th, 2015, 2 black holes collided. One contained 36 solar masses, the other 29. They had orbited each other for millions of years, spiraling closer as gravitational waves carried away their orbital energy. In the final fraction of a second before merger, they orbited each other 250 times per second. Their event horizons touched. They merged. The collision released 3 solar masses worth of energy as gravitational radiation. For that brief moment, the merger radiated more power than all the stars in the observable universe combined. The gravitational waves traveled outward at light speed. 1.3 billion years later, they reached Earth and caused the arms of the LIGO detectors to shift by 1/10,000th the diameter of a proton. Black hole mergers represent the most energetic events the universe produces. Supernova explosions release approximately 10 to the 51 ergs. Gamma-ray bursts release comparable energy but focus it into jets. Black hole mergers release 10 to the 54 ergs or more, with the energy emerging entirely as gravitational radiation. That radiation does not interact strongly with matter. It passes through planets, stars, galaxies without slowing. But it carries information about masses, spins, orbital parameters. Information encoded in the waveform detected by gravitational wave observatories. The merger process follows predictable stages. First, the inspiral. 2 black holes orbit each other, gradually approaching as gravitational radiation carries away energy. This phase can last millions of years for stellar mass black holes or billions of years for supermassive black holes. The orbital frequency increases as the separation decreases. Eventually, the black holes approach close enough that their orbital period drops to seconds, then milliseconds. The inspiral accelerates. The second stage is the merger itself. The event horizons touch. Space-time geometry becomes too complex for simple description. Numerical relativity simulations running on supercomputers are required to model what happens. The 2 black holes merge into a single, distorted black hole. The distorted black hole is not spherical. It wobbles, oscillates, radiates gravitational waves from its surface deformations. This phase lasts milliseconds for stellar mass black holes. The third stage is ring down. The merged black hole settles into a stable configuration. The oscillations decay. The gravitational wave amplitude decreases exponentially. Within seconds, the new black hole becomes quiescent. A larger black hole, containing the combined mass of both progenitors minus the mass radiated as gravitational waves. The event horizon is larger. The angular momentum is the sum of the progenitors' angular momenta, and spacetime around the merged hole returns to the static geometry described by the Kerr solution for rotating black holes. Neutron star mergers follow similar stages but with crucial differences. Neutron stars have matter. That matter can be disrupted, ejected, heated. When two neutron stars spiral together and merge, the outcome depends on the total mass. If the combined mass exceeds the Tolman-Oppenheimer-Volkoff limit, the merger produces a black hole. But before the black hole forms, the merger ejects matter. Neutron-rich material expelled at velocities approaching 20% of light speed. That material undergoes rapid neutron capture, synthesizing heavy elements. The August 2017 neutron star merger, designated GW170817, demonstrated this process observationally. LIGO and Virgo detected the gravitational wave signal from the inspiral and merger. The signal lasted approximately 100 seconds, much longer than black hole mergers because neutron stars are larger and merge at lower orbital frequencies. Approximately 2 seconds after the merger, the Fermi Gamma Ray Space Telescope detected a short gamma ray burst from the same direction. Then, 11 hours later, optical telescopes detected a kilonova in the galaxy NGC 4993. The kilonova resulted from radioactive decay of heavy elements synthesized during the merger. The ejected neutron-rich material, free from the neutron star's gravity, underwent rapid neutron capture. Neutrons bombarded atomic nuclei, creating progressively heavier isotopes. Uranium, plutonium, gold, platinum, elements that cannot be synthesized in stellar cores or ordinary supernovae because those environments lack sufficient neutron densities. The newly synthesized elements were unstable. They decayed radioactively, releasing energy. That energy heated the ejected material, causing it to glow. The glow peaked in optical and infrared wavelengths days after the merger, then faded over weeks. Spectroscopic observations of the kilonova confirmed the presence of heavy elements. The spectrum showed absorption features consistent with lanthanides and actinides, elements with atomic numbers exceeding 57. These elements are rare on Earth, but their presence in the kilonova spectrum proved that neutron star mergers produce them. Every gold atom on Earth was created in a neutron star merger, or supernova, billions of years ago. The gold in your jewelry, if you wear any, originated in an event of unimaginable violence when two dead stars collided. Supermassive black hole mergers operate on vastly larger scales, but slower timescales. When two galaxies merge, their central supermassive black holes eventually sink to the center of the merged galaxy through a process called dynamical friction. But bringing them from galaxy-scale separations down to merger requires time. The black holes orbit each other at distances measured in light years. At those separations, gravitational wave emission is negligible. The orbit decays primarily through interactions with stars and gas. Stars passing near the binary receive gravitational kicks, carrying away energy. The black holes spiral closer, over millions of years. At separations below 1 light-year, gravitational wave emission becomes significant. The black holes enter the inspiral phase. But even then, the timescale to merger can be thousands of years for million solar mass black holes, or millions of years for billion solar mass black holes. The orbital frequency is low, microhertz range, too low for ground-based detectors like LIGO to detect. Future space-based detectors, like LISA planned for launch in the 2030s, will observe these systems. When supermassive black holes finally merge, the gravitational wave amplitude is enormous. The merger of 2 billion solar mass black holes would be detectable across the observable universe. The strain amplitude would exceed the sensitivity threshold of LISA, even from redshifts approaching 10. These mergers are rare, perhaps one per year in the observable universe, but they are detectable across cosmic distances because of their enormous masses and correspondingly large gravitational wave amplitudes. The environment surrounding a supermassive black hole merger is catastrophic. Gas and stars orbit the binary at distances measured in light days or light weeks. As the black holes spiral together, they disrupt those orbits. Stars are ejected at high velocities. Some are captured by one of the black holes and tidally disrupted. Gas is heated by shocks and friction. The region lights up in X-rays and optical wavelengths. The accretion disk becomes unstable. Material flows inward erratically. The system brightens and dims. Then, at merger, the gravitational wave burst is released. Space-time ripples propagate outward, and the merged black hole, now more massive and rapidly spinning, settles into a new configuration. Galaxy mergers that bring supermassive black holes together also trigger star formation. Gas clouds collide, shock waves compress the gas, stars form at elevated rates. But near the merging black holes, star formation is suppressed. The radiation environment is too harsh. The gravitational perturbations are too strong. Close to the black holes, within light years, no stars can form. Existing stars are ejected or disrupted. The region becomes a zone of destruction. Some black hole binaries never merge. The final parsec problem describes a theoretical difficulty. Once two supermassive black holes approach within approximately 1 parsec of each other, dynamical friction becomes inefficient. Too few stars remain in the central region to carry away the binary's orbital energy. Gravitational wave emission is still weak at parsec separations. The binary stalls. According to some models, it might orbit for billions of years without merging. Other models propose solutions: gas accretion, interactions with a third black hole, triaxial galaxy potentials, mechanisms that could bring the black holes closer and enable merger. The debate continues. Observations suggest some galaxies host binary supermassive black holes, periodic variations in quasar brightness, dual-active galactic nuclei separated by kiloparsecs. These systems are in the early stages of merger. The black holes have not yet approached close enough for gravitational waves to dominate, but they are approaching. Over millions of years, they will spiral together. And eventually, barring solutions to the final parsec problem, they should merge. The merger of supermassive black holes reshapes galaxies. The gravitational wave recoil, caused by asymmetric emission of gravitational radiation during merger, can kick the merged black hole out of the galactic center. Velocities exceeding 1,000 kilometers per second are possible for certain mass ratios and spin configurations. A black hole ejected at that velocity could escape the galaxy entirely. More commonly, the recoil displaces the black hole by tens or hundreds of parsecs. The black hole oscillates around the galactic center for millions of years before friction and dynamical interactions return it to the center. These collisions and mergers are not anomalies. They are natural consequences of gravity and orbital mechanics. Black holes in binary systems must eventually merge. neutron stars in binary systems must eventually merge. The timescales are long, but the outcomes are certain, and each merger releases energy on scales that dwarf anything else the universe produces. Energy emerging as gravitational waves that ripple through space-time, carrying information about the most violent events in the cosmos. But detecting these events requires instruments capable of measuring space-time distortions smaller than atomic nuclei across distances of kilometers. 4 kilometers long. That is the length of each arm of the LIGO detectors in Hanford, Washington, and Livingston, Louisiana. 4 kilometers of ultra-high vacuum chambers housing laser interferometers sensitive enough to detect gravitational waves that change those arm lengths by 1/10,000th the diameter of a proton. The detectors measure space-time distortions of approximately 10 to the negative 21 meters. That is a fractional change of 1 part in 10 to the 21. To put that in perspective, if you tried to measure the distance to the nearest star, Proxima Centauri, with this precision, you would need to be accurate to within the width of a human hair. Detecting cosmic horrors requires overcoming fundamental measurement challenges. Most of these objects are distant. Many emit little or no light. Some are obscured by dust. Others hide behind the galactic plane in the zone of avoidance, and the effects we seek to measure are often subtle. A magnetar 7,000 light-years away appears as a faint X-ray source. A black hole not actively accreting emits nothing. A supervoid reveals itself only through the absence of galaxies or subtle effects on background radiation. These are not bright, obvious phenomena. They are whispers in the cosmic noise. Gravitational wave detection represents one solution to the measurement problem. Gravitational waves interact weakly with matter. They pass through Earth without scattering or absorption, but that weak interaction makes them nearly impossible to detect. LIGO achieves detection through extreme precision and careful control of noise sources, seismic vibrations, thermal noise in mirror coatings, quantum fluctuations in the laser light itself. Each noise source must be understood, modeled, and either eliminated or accounted for in data analysis. The detectors operate at the edge of what current technology allows. The September 2015 black hole merger detection succeeded because the signal was strong and the detectors had just achieved design sensitivity after years of upgrades. The gravitational wave strain peaked at approximately 10 to the negative 21. The frequency swept from 35 Hz to 250 Hz over 0.2 seconds. That chirp pattern matched theoretical predictions for black hole mergers with remarkable precision. The detection was clear, unambiguous, but most gravitational wave signals are weaker. They require more sensitive detectors or longer observation times to accumulate sufficient signal-to-noise ratio. Radio telescopes penetrate dust and gas that block optical light. The zone of avoidance obscures the great attractor in visible wavelengths, but radio observations can penetrate the galactic plane. Radio surveys have mapped galaxy positions behind the Milky Way's disk, revealing the mass distribution in previously obscured regions. These observations confirmed that a massive concentration of galaxies exists in the direction of the great attractor. Not a single object, but a supercluster. Thousands of galaxies concentrated in a region tens of millions of light-years across. X-ray telescopes detect neutron stars and black holes that would be invisible in optical wavelengths. The Chandra X-ray Observatory, launched in 1999, has imaged supernova remnants, pulsar wind nebulae, and active galactic nuclei across the sky. X-rays reveal hot gas, accretion disks, jets, regions where matter reaches temperatures exceeding millions of degrees. These are the signatures of extreme physics, of gravitational energy converted to thermal energy, of magnetic fields accelerating particles to relativistic speeds. But X-rays do not penetrate Earth's atmosphere. X-ray telescopes must operate in space. Chandra orbits Earth in a highly elliptical orbit, reaching 1/3 of the way to the Moon. At that altitude, above the atmosphere's absorption, the telescope can detect X-rays from distant sources. The observations require exquisite control. The telescope's mirrors are polished to nanometer precision. The pointing accuracy measures arc seconds. These specifications are necessary to resolve X-ray sources and distinguish individual objects in crowded fields. Gamma ray detection presents even greater challenges. Gamma rays are absorbed by the atmosphere, but that absorption produces secondary particles detectable at ground level. When a high-energy gamma ray strikes the upper atmosphere, it creates an electron-positron pair. Those particles radiate more gamma rays through bremsstrahlung. Those gamma rays create more pairs. The cascade grows. Hundreds of particles reach ground level, arriving within nanoseconds of each other. Arrays of detectors measure the cascade's properties: direction, energy, timing. From these measurements, physicists reconstruct the original gamma ray's properties. The detection of GRB 190-114C's tera-electronvolt photons use this technique. The magic telescopes in the Canary Islands detected the particle cascade triggered by gamma rays from the burst. The cascade's properties indicated photon energies exceeding 1 trillion electron volts, the highest energy photons ever detected from a gamma ray burst. The detection required not only sensitive instruments, but also rapid response. Gamma ray bursts fade quickly. Observations must begin within seconds to minutes of the burst. MAGIC received an alert from the SWIFT satellite and slewed to the burst location within 57 seconds. Gravitational microlensing reveals objects that emit no light: rogue planets, isolated black holes, brown dwarfs. When one of these objects passes between Earth and a background star, its gravity bends light from the star. The star brightens temporarily as light paths converge. The brightening follows a predictable curve: symmetric, achromatic, the same in all wavelengths. The duration depends on the lens mass and velocity. For an Earth mass rogue planet, the brightening lasts hours. For a Jupiter mass planet, days. For a black hole, weeks to months. Surveys monitoring millions of stars can detect these rare events. The Optical Gravitational Lensing Experiment, OGLE, monitors stars in the Galactic Bulge and Magellanic Clouds. Hundreds of microlensing events are detected each year. Most are caused by stars, but some show anomalies indicating planetary companions or free-floating planets. Analysis of the light curves reveals the lens mass and distance. Statistical studies of microlensing event rates constrain the population of dark objects in the galaxy. But microlensing has limitations. It detects objects only when they happen to cross the line of sight to a monitored star. The probability of alignment is small. Most rogue planets never produce detectable events. The technique is statistical. It reveals population properties, but not individual object locations. We know rogue planets exist. We know approximately how many. But we cannot point a telescope at a specific rogue planet and observe it unless it happens to be lensing a background star at that moment. Cosmic microwave background observations reveal supervoids through the integrated Sachs-Wolf effect. Photons from the CMB traveling through a void experience gravitational redshift as they enter and blueshift as they exit. In a static universe, these effects would cancel. But the universe expands. Voids expand faster than average. The gravitational potential weakens as photons cross the void. The exit blue shift is smaller than the entrance red shift. The net effect is a slight temperature decrease. The Planck satellite mapped the CMB with sufficient precision to detect these temperature anomalies. Each cold spot in the CMB corresponds to a supervoid along the line of sight. The Eridanus supervoid produces a cold spot approximately 5 degrees across. The temperature deficit is approximately 70 microkelvins relative to the mean CMB temperature of 2.725 Kelvin. That is a fractional difference of 2.5 parts in 100,000. Detecting such subtle signals requires instruments with extraordinary sensitivity and careful control of systematic errors, foreground contamination, instrument noise, calibration, and uncertainties. All must be understood and corrected. Neutrino detection offers a window into processes hidden from electromagnetic observations. Supernovae produce vast numbers of neutrinos. Core collapse releases 10 to the 58 neutrinos in approximately 10 seconds. Most pass through the surrounding stellar material without interacting. They escape carrying information about conditions in the core. The neutrinos from supernova 1987A, detected by Kamiokande and IMB detectors, arrived 3 hours before the optical brightening. They provided the first direct observation of a supernova's core collapse. But neutrino detectors must be enormous to detect enough events for meaningful analysis. The IceCube Neutrino Observatory at the South Pole instruments 1 cubic kilometer of Antarctic ice. Optical sensors detect Cherenkov radiation produced when neutrinos interact with ice nuclei. The interactions are rare. Trillions of neutrinos pass through the detector for each detected event. But the large instrumented volume and long observation time compensate. IceCube detects hundreds of neutrinos per year from cosmic sources. Gamma-ray bursts, active galactic nuclei, possibly supermassive black hole mergers. Each detection provides information electromagnetic observations cannot. Multi-messenger astronomy combines observations across all channels. Electromagnetic radiation, gravitational waves, neutrinos, cosmic rays. The neutron star merger detected in August 2017 exemplified this approach. Gravitational waves from LIGO and Virgo, gamma rays from Fermi, X-rays from Chandra, optical observations from dozens of telescopes, radio observations weeks later. Each wavelength revealed different aspects of the event. The gravitational waves showed the inspiral and merger. The gamma rays showed the jet. The optical kilonova showed heavy element synthesis. The X-ray and radio afterglow showed interaction with the surrounding medium. These observations required global coordination, alerts distributed within seconds, telescopes slewing to target coordinates, observers analyzing data in real time and sharing results. The success demonstrated that multi-messenger astronomy is not just possible, but powerful. Complementary observations provide insights no single instrument can achieve. And future detections will benefit from even better coordination and more sensitive instruments. But despite all these techniques, much remains hidden. Dark matter comprises 85% of the universe's matter, but has never been directly detected. We observe its gravitational effects, galaxy rotation curves, gravitational lensing, cosmic microwave background fluctuations. All require dark matter, but we do not know what it is. The measurement problem for dark matter is fundamental. If it interacts only gravitationally, detection requires either enormous mass or long integration times or both. Current experiments push the limits of technology and still find nothing. The cosmic horrors we have measured represent only what we can detect. What remains beyond our instruments' reach is unknown. Smaller voids, isolated black holes drifting through intergalactic space, rogue planets in interstellar regions far from stars where microlensing is unlikely, magnetars with radiation beams pointed away from Earth. All these exist but remain invisible. We map the universe through what we can measure, but the map is incomplete, and what exists beyond the map's edge remains, for now, unknowable.